Why does a metal spoon in a bowl of soup feel hotter than the bowl itself, even though they're the same temperature? I'll teach you how heat travels through solids and fluids, and then we'll learn how to calculate energy loss by conduction. So first, let me introduce to you a concept. Conduction is the direct transfer of heat through a material due to molecular collisions. What does that mean? So hotter molecules jiggle faster, and when they bump into neighbors and they collide, they pass on energy. This ripple transfers heat through the object. So conduction is the microscopic handoff of energy from molecule to molecule. There's an equation for it. I'll write it out here. This is the rate of heat flow, and it's equal to thermal conductivity represented by K. This is a material property, so it depends on the material, times A, which is the cross-sectional area. So if you got a cube and you cut it in half, if you look at the cross-section and the area of that cross-section, that's A. The difference in temperature divided by the thickness or length of the material. So if there's more area, that means there's more room for heat to flow. If there's more thickness, then there's more resistance, and materials with higher K, like metals, conduct heat the best. Here's some good conductors examples. Copper, good. Steel, good. Here's some bad ones, which we call insulators. Wool, air, foam, and wood. These are terrible conductors. These are strong thermal conductors. That means heat flows through them more efficiently compared to these, which are insulators. Let me show you a value called R. R is equal to the length divided by K. And what R represents, the higher the R, the better the insulation, which means that there's less heat transfer between objects. And higher insulation means less heat transfer between objects, which means you will stay warmer. That's why I'd rather a fluffy wool blanket than a steel blanket. Here's an example problem. You've got a glass window. Its area is 2.4 meters squared because it's 1.2 meters by 2 meters wide. The thickness is 4 millimeters. The thickness means that it is 3D because area decides how wide the heat can spread and thickness decides how far it has to travel. Anyway, inside your room, so on one side of the window, it's 22 degrees Celsius. But on the outside, it's 5 degrees. Glass has a thermal conductivity of 0.84 watts per meter Kelvin. That's the unit. And we're trying to find the rate of heat loss, aka watts, through this glass window using conduction. Let's write our formula first. And if you haven't got the free cheat sheet in the description, I highly recommend it. You don't have to flip through your notes anymore. Our equation was this. We know all of these values, and we're looking for the heat lost. And the heat that's lost is represented by this value here, because we're given everything on the right-hand side. So the power lost as heat would be how much energy is leaking out every second through conduction. Let's plug in our numbers. So for K, we have 0.84 for glass. For A, which is the area, it's 2.4. That's the area of our glass. For the change in temperature, well, it's 22 inside versus 5 outside. So the change in temperature is a 17-degree difference. The length is 4 millimeters. And 4 millimeters converted to meters is 0.004. There we go, we're ready to solve. This is equal to 8,568 joules per second, or watts. So every single second, this amount of heat leaks out through the window, just because there's a 17-degree difference. Now imagine every single window, every single night. That's why insulation matters. Otherwise, you're going to get cold. The next concept I need to teach you about is convection. Convection is the bulk movement of heated fluid, liquid, or gas from one place to another. So imagine this. If you put your hand above a candle flame, you feel the heat rising. But it's not conduction because your hand isn't touching anything. It's not radiation alone. What you're feeling is hot air rising. What's happening here is the air near the flame, so all the air around it, heat up. Hot air is less dense, so it rises, and then cooler air, colder air above it, sinks to take its place. This creates a cycle. It's called a convection current. Hot stuff goes up, cold stuff goes down. The fluid moves, carrying heat with it. The molecular explanation is that in conduction, only energy moves. Energy is transferred from one molecule to another. In convection, the molecules themselves move, which brings energy with them. Some real-world examples are boiling water, so the bubbles rise and the cooler water falls. In heating systems, so heaters that you might have in your bedroom, the warm air rises to the ceiling. And your blood, so your heart, always pumping blood, pumps warm blood from your core to your skin to cool you off. Conduction is like energy handshakes. Convection is moving the entire group, and the fluid flows carrying heat with it. Let's go through an example problem. Why does a hard tile on the floor of your kitchen feel colder than the fluffy carpet in your bedroom? Here's a situation. You're walking barefoot in your house. The room temperature itself is constant, 21 degrees Celsius everywhere. But the tile feels way colder than the carpet. Why? The answer is because of conduction, not convection. Tile is a much better thermal conductor than carpet, so it pulls heat from your foot way faster. So even if both are 21 degrees Celsius, the tile makes your skin lose energy quicker. Your nerves detect this rapid energy loss as cold.